Professor.
Good morning.
Good morning. Can you look at my assignment 6 after the class?
Can I look at it?
Yeah, I'm having problems.
I can do that. Yeah.
Thank you.
All right. Good morning, everyone. Today we're going to discuss NP completeness, which brings us to a part of the course which is important, but in a certain way it's a bad, because until now, most of the problems that we've looked at were problems that could be solved, not only solved, but solved in a reasonable amount of time. By reasonable, we usually define that to mean polynomial time. What we're going to discuss today are algorithms and the theory related to the algorithms that cannot be solved in polynomial time. All right, or I should say that a little bit differently. We don't know how to solve them in polynomial time, and we suspect that they cannot be solved in polynomial time. So that is the topic for today. Also, some courses of 320 will discuss it there. And of course, we have an entire course in the graduate program called Computability and Non-Computability. Right, so our starting point for today's discussion is, what do we mean when we say a program or a problem has an efficient solution? What does it mean to be efficient? Is it n log n? Is it n squared? Is it n cubed? Is it polynomial? How do we decide that? So one possibility is to say that if we know the problem has a lower bound, okay, so I'm saying ignoring any particular algorithm, right? If the problem has a known lower bound, and we can get that or close to it, then that means it's a good solution. For example, right, we can prove using something called the decision tree model, and we did that back in, I think it was our 4th lecture, Sorting Algorithms 2. We discussed decision tree model. So we can prove that any comparison-based approach to searching is going to take at least log n. And any comparison-based approach to sorting is going to take at least n log n. So if we have an algorithm like binary search that searches in log n time, or we have an algorithm like merge sort that sorts in n log n, so that's good, right? That means we have a good algorithm. As opposed to if you have an algorithm that sorts in n cubed, that's probably not such a good algorithm, because we know that, n log n is lower bound, so we would expect, something a little closer to that. So it turns out that the criteria we use, from a theoretical perspective, what makes an algorithm efficient is that it be done in polynomial time. Okay, that doesn't mean it's the optimal algorithm, but that's where we draw the line between what we call tractable and intractable. Okay, so the term we often use is tractable. Okay, tractable means that it can be solved in a reasonable amount of time. So the threshold is polynomial time. Okay, meaning something like x to the 5th or x to the 4th or x cubed, right? N log n would be included in that because it's not bigger than n squared. All right, but there's another piece to this, and that it is in a deterministic model of computation. Does anyone know what that word means?
The output will always be the same if the input's the same.
Okay, so the output is always the same if the input is the same. And in terms of the mechanics of that, it means that for any given state that you're currently in and a specific piece of the input, it will always do the same thing, right? So let's take a look at this little state diagram over here. If I'm in S1 and I get a 0, I move to S2. If I'm in S2 and I get a 0, I move to S1. If I'm in a state S2 and I get a 1, I stay in S2. If I'm in S1 and I get a 1, I stay in S1, right? So for each state, there's only one thing I can do, all right? I should say, let me say it differently. For each state, for each possible input in that state, there's only one thing I can do. We call that P. Now, we also have something called NP, which is obviously very important if you're giving a lecture on NP completeness, but many people, many students do not understand what NP is. All right, so usually it's, they've heard the term, but they haven't learned about it. Sometimes they even don't understand after they learn about it. So what is NP? It does not stand for non-polynomial. It stands for non-deterministic polynomial. And what does that mean? It means that the long way of saying it is the problem can be solved in polynomial time in a non-deterministic model. What does that mean? So if you look at the picture here, this is an example of non-determinism. Everyone see that? So if I'm in state P and I get a 0, then I necessarily have to go, stay in state P. But if I get a 1, I have a choice, right? This arc, this transition allows me to stay in state P. But there's another transition that says that I can go to state Q if I want. And the machine, this is where it gets a little interesting. The machine is supposed to know how to decide, right, which is the right way to go in that situation. Now, obviously, that's allowing the machine to be smarter than machines usually are, right? Machines are not very good at guessing correctly. They're good at following instructions most of the time, right? So that's why we don't really go by non-deterministic models, because the models that we actually can implement, that we can build, are deterministic models, right? If this is where you are and this is what you get, this is what you do. You don't, pick up, have 4 things and guess correctly. Now, this is somewhat at odds with something we're going to talk about. We've talked about before many times, and we have a dedicated lecture. It's called randomized algorithms. And randomized algorithms, we use randomization, okay? But that's different. Randomization is, in a sense, a kind of determinism, right? Because you're saying, here's a random variable, get it a value, and depending on what the value is, this is what you do. So we're giving it very definitive steps what to take. It's not, guess, right? It's saying if the random number is between 0 and 5, you're going to do this. And if it's between 6 and 10, you do that, and so on and so forth, right? So even with the randomization, right, it's still considered a deterministic kind of model, technically speaking. Okay, so I have this slide here. This slide is, in a certain sense, at odds. Okay, if there is an algorithm, is it truly random? How is it truly random? Well, the randomization means we are using a random number to guide our decision. So that's also kind of input. In other words, the input isn't only the input, but it's also our randomization is used to help us make a decision. All right, so we'll talk more about randomization in a different lecture, about randomization. All right, so the purpose of this slide is, in a sense, counterproductive. What do I mean by that? So I just finished telling you that the line that we're going to draw in the sand is between polynomial time and things that take more than polynomial time, what we might call super polynomial or super polynomial time, right? More than polynomial time. The purpose of the slide, which you've seen before in one of the early lectures of our course, is that the difference between n squared and n log n makes enough difference between, practically solvable and not practically solvable, right? The n log n algorithm, for a reasonable kind of problem, it can be done in 1 minute. And the same problem using an n squared algorithm would take 65 years. Okay, so even though I just finished telling you that we draw the line between polynomial and non-polynomial, in reality, even an n squared algorithm, which sounds like it's a pretty good polynomial, is not so good unless your input is more manageable. As many of you have discovered in this course, right, when you do n squared algorithms and you make your n big, not crazy big, but even like 10,000 or 100,000, it doesn't finish. Some of you discovered that in sorting. Some of you discovered that in the dynamic programming assignment, right? When your string was too long, it just, it took hours, and we don't have even hours is a long time in a six-week course. All right. So this sort of begs the question, which is, okay, so if I just finished showing you that polynomial time, even n squared, isn't so good, why are we drawing the line there? All right. So here are a few reasons, right? Number one, it's an upper bound on tractability. What do I mean by that? It means that if it's more than polynomial, it's out of the picture. Okay, it's clearly untractable. So it doesn't mean that every polynomial time is so practically tractable, but it does mean that if it's more than that, just forget about it. Okay, it's not going to work unless there's a really teeny tiny kind of input. Number two is a closure of polynomial time operations. I'm going to come back to that in a moment because that requires a little bit more explanation. And then models of computation, which means that if I can do it in polynomial time one model, I can do it in polynomial time another model, right? Let me give you an example of that. So I don't know who here has taken 320, but in 320 you learn about Turing machines. Okay, basic idea of a Turing machine is you got a tape and you got a tape pad and you move along the tape to the left and the right and you do things based on what you see on the tape at that position. All right, so the standard Turing machine involves one tape, but there are Turing machines that have multiple tapes. There are machines that are multiple tapes with one tape pad, and there are multiple machines with multiple tapes and multiple tape pads. So the one of them we call multi-track, the other we call multi-tape. All right, you don't need to really understand that in this course, but for those of you who have taken that course, you'll appreciate it in this context. So if you take something that's polynomial time on the multi-tape machine, it will still be polynomial time on the single tape machine. It might be a higher degree of polynomial, it might go from, let's say, n to n squared, but it will still be polynomial time. So it allows you to sort of swap between different models and still be considered, tractable. All right, let's go back to the second bullet point here. So if I take two polynomials and I add them, I get a polynomial. Everyone agree with that? Okay, so we call that closure under addition. If I take two polynomials and I multiply them, I get a polynomial. If I take two polynomials and I compose them, what does compose them mean? It means I take P1 as a polynomial and I apply that to another polynomial of X. Right, so I take the output of one polynomial and I plug that into another polynomial. That's what we call composure. Okay, sometimes it's written differently with a dot. It's written like, I don't have a dot on my machine. Well, it's usually with a circle in the middle. But anyway, there are other ways of writing composure. Right, so what does this have to do with time complexity? The answer is, if I concatenate two programs, meaning I have a program, then I run another program, and the first one has time complexity X, and the second one has time complexity Y. What's the total time complexity? X plus Y. You know where we saw that? We saw that a lot in graph algorithms, right? We had an initialization part of the program, and then the main part of the program, like in Floyd's algorithm and Dijkstra's algorithm. So what is the total complexity? You take the time complexity of the first chunk, time complexity of the second chunk, you add them together. So if each one is a polynomial and I add the polynomial, I will get a polynomial. Multiplication, if I nest one program inside another one. So what did we do yesterday? We took Dijkstra's, let's say, single source shortest path algorithm, and we put that inside another loop to solve the all pair shortest path problem, right? So that's nesting, okay? So what do? You take the time complexity of the inner one times the time complexity of the other one, which the outer one was O of n times whatever's on the inside gives you the time complexity. Or if we have one program that, let's say, generates all the permutations, and then we take all the permutations and we make that the input to another program, what's the time complexity? That's equivalent to doing composition of the polynomials. So the point is, if everything we start with is polynomial and we apply addition, we apply multiplication, we apply composition, we remain a polynomial, it's all in the same family, right? It's all polynomials. So it allows us to, piece together algorithms in such a way. Again, from a practical perspective, it's really not about polynomial versus non-polynomial, because many polynomial time algorithms are just too darn expensive. All right, but that's where we draw the line. So that's why we have to talk about this. Okay, so here I just give an example of the multi and single tape, right? So here's your classic example of a 1-tape machine. Here's an example of a 3-tape machine. And the point is, and you learn more about this in 323 generally, I'm sorry, in 320, is that, you know, an algorithm that you might be able to do in order a linear time in the 3-tape machine might take quadratic time on a multi-tape machine. And you can actually prove those results. All right. So these different problem classes are going to be what we're going to discuss today for the most part, right? We already talked about P, which were the problems that can be solved deterministically in polynomial time, and NP, which are the problems that can be solved non-deterministically, right? Where we have a machine that can guess correctly, all right? Another way to think about NP is solutions that can be verified in polynomial time. So let me give you an example of that, right? Does everyone know what graph coloring is? Right, graph coloring is, you know, coloring the vertices of a graph with different colors so that no two adjacent vertices, right, that have an edge between them have the same color, right? So you can't have two vertices that are blue if there's an edge between them, all right? So a interesting problem in computer science and graph theory is, you know, how many colors do I need for a graph? So to figure out the optimal number is not so simple. Even to figure out, can I do it with, let's say, 4 colors? There are some theorems about this, by the way, but I can do it with 4 colors is not so simple. But what would happen if someone told you, here is a coloring of the graph, and I did it with 3 colors? So do I believe that? Does it work? So that's easy to check, right? Because I just run through every edge and I look, do they have the same color or not? If I can get through all the edges, which I can do in O of E time, and none of them have the same color on both endpoints, then I know it's correct. So sometimes I have an algorithm, a problem that to solve it, I don't know how to do it in polynomial time. But if someone gives me a solution and says, here, you check that it works, I can. All right, then we have NP hard, right? NP hard are problems that are the hardest problems available in NP, and it includes unsolvable. Okay, so Ellie is asking, I thought you could do every graph with 4 colors. And the answer is yes or no. So do you know anything more about that statement? There is such a statement. There is such a theorem.
I mean, I don't know much. I just thought that like that was the theorem was that you can use 4 colors in any graph so that no 2 colors are touching each other.
Okay, hold on 1 second here. I'm looking at my library, which I recently reorganized, and I'm trying to figure out where that book is. Aha, I found it. Can everyone see this book? Can you read the
4 color problem?
Yeah, the 4 color problem. So it's all about this very thing. Okay, does anyone know why this is important enough? Okay, look at the subtitle, Assaults and Conquest. Okay, I don't have a book like this on other theorems. I might have one on Fermat's last theorem, maybe I have a book on that. But do anyone know what's so special about this particular problem? Not why I bought it. Why is someone writing a whole book about? Because it was the first major proof that was done by a computer. Or let me say that differently. That was done by a computer that had not been done by a human being. Okay, so that created a philosophical issue, which is if it's so complicated that only a computer can verify it, is that considered proof? All right. So the answer is there is something called a 4-color problem, right? It does say conquest, which would suggest that it was solved. And it was solved with a computer, but there's a catch to it. It's a planar graph, okay? A graph that can be drawn in the plane without, you know, overlapping edges. So beyond that, can someone tell me how you can easily come up with a graph that requires more than 4 colors? So you don't have to be a rocket scientist for this. So come up with a counterexample to the idea that every graph could be done with 4 colors. Graph we did in our class. Okay, I'm not looking for something crazy.
I mean, if you have like kind of like a circle with like 5 pieces in it, they're all
Okay,
touching.
there you go. Circle is not a problem. Circle you can usually do with 2 colors, most 3, cycle graph. K5, what does K5 mean?
Where every single like 5 nodes are all touching the other 4.
Okay, so it's usually drawn like a pentagon, doesn't have to be a pentagon, right? So it's a complete graph of order 5, right? 5 vertices, each one is adjacent to every other one. Okay, can't do that. Can't do that with the 4 colors, right? Because I got this vertex, and it's going to be adjacent to 4 other vertices. So you say, okay, so I'll make them all the same color, but they're all adjacent to 4 other things, right? So I can't do that with 4 colors. I need 5 colors for that. But why is that an exception? Because it's not a planar graph, okay? K5 is the first complete graph that's non-planar. K4 is planar, all right? So the answer is yes, if it's planar, but even that was not so obvious. That's why we have this this book over here. Okay, so let's go back, all right? So there are problems that are unsolvable, okay? Who remembers an example of an unsolvable problem?
Halting problem?
The halting problem, correct. And did we watch the video yet? Did I show you that video,
No.
that fun video? Okay, we're going to watch the video now. All right. Before we do that, can someone give me another example? I think we mentioned another example at the beginning of the semester. How about the Diophantine equation problem? Okay, see if I can even spell that. Diophantine equation problem. Okay, what is that? It means, are there integer solutions to a polynomial equation, right? A polynomial with different exponents and different variables, and I want to know, can I assign integer variables to these x's to make it equal to 0? So it turns out there's no solution to that in general. There are polynomial time solutions for certain polynomials, some of which you know, like the quadratic equation, right? We can figure out the quadratic equation very simply, and we can check if it's an integer or not, right? So those are 2 famous unsolvable problems. There are others. A lot of them are related to the halting problem. So I have a book here. Anyone use this book? Okay, so we have 2 sections on the halting problem, and then we have other problems that are derived or related to the halting problem, right? So those are unsolvable as well. So we can basically show if you could solve those, you could solve the halting problem. Halting problem is provably unsolvable. All right. So let's just finish this slide here. So we have the NP-complete. NP-complete problems are problems that are between both an NP and an NP-hard. That means they're at least as difficult as the other NP problems, which means they're at least as difficult as the other NP-complete problems. This P equals NP is a major problem in computer science. And let's see, I have a slide about that. All right, I'm going to come back to this in a second. So here is 2 people are very involved in P equals NP. And I want you to see, this Clay Mathematics Institute, not to be confused with Carnegie Mellon. CM is not Carnegie Mellon, right? These are one of the Millennium Problems. And if you solve the problem, and you know what you get $1 million. And I will throw in an A+. So anyone who solves the P versus NP problem before the end of our course will get an A+ from me, even if they didn't do assignment 6. Okay, all right. That said, I recommend that you do all your assignments and you prepare for your exam, because it's not so likely you're not going to solve that. Okay, let's just come back to this, and then we're going to watch our video. So we don't know if P equals NP. That's why someone's offering $1 million to anyone who can figure it out. So depending on whether P equals NP, that determines which of these 2 pictures is correct. All right, so we're going to start with the one on the right, on the left, which is the one most people believe is correct. Most people think that P and NP are different, meaning it's harder to solve a problem that can only be done with a deterministic model, and the ones that can't be done in a deterministic model, right? All these problems we have, we think that they really take more than polynomial time. So if that is true, that means that we have P, which is in NP. Again, these are the ones that can be solved in deterministic polynomial time. These are the ones that can be solved not necessarily in deterministic, but at least in a non-deterministic model. Then we have NP complete problems, which are in NP, but they are also in NPR, meaning they're at least as difficult as these. And then we have the NP hard, some of which are more difficult than the NP complete problems. Okay, they're more difficult, including the unsolvable ones. Okay, so I promised you the video. So we're going to watch the video. And this is a lots of fun video. I have to reshare my screen because I need to reshare it with the sound. Okay, so here we go. I'm going to share my screen. Okay, good. Now I need to find the video. Come on. Okay, there we go. Okay, and by the way, if you like this video, the authors of this video have a few other ones as well, and they're just a lot of fun to watch. Okay, here we go. So the most fun 7 minutes of our course.
It's hard to believe that Mint Mobile can be good at just $15 a month. So, as Mint's new owner, I brought in one of our first and oldest customers.
Here we go. I'm just going to try to get rid of this thing at the bottom. Can you hear it?
Yeah.
Yeah, you can hear it. All right. Okay, so first we have some polynomial time algorithms. We have some not so polynomial time algorithms. And then we have some unsolvable problems.
This is Computing Machine A. A solves problems in arithmetic. It receives a problem written on paper, and it prints the answer.
Okay, by the way, for the final exam, everyone has to...
It always prints the right answer.
I'm sorry?
Here's another computing machine, C. C plays checkers. It receives the current state of the board, and it prints how it would move one of the red pieces. C plays checkers so well, it will never lose a game. A and C are machines we can already build today, and computers keep getting smarter and smarter, so will they eventually be able to do everything? Let's feed A with a board of checkers. A was not designed to handle this kind of input, and when it tries to process it, it gets stuck. The same thing happens to C when fed with a question in arithmetic. Let's draw a blueprint of A. This blueprint is detailed down to the level of the logic circuits, and it fully defines how A works. We are now finally ready to introduce a marvelous machine called H. H solves what is known as the halting problem. It can analyze the blueprint of another machine and determine which inputs are good for it and which will cause it to get stuck. It receives the blueprint of the machine to be tested and an input to test it with. Based on the blueprint, H simulates the given machine on the given input, and then determines if it gets stuck or not. H solves the halting problem perfectly. It always prints the right answer. Here are two more examples with the blueprint of the checkers machine.
Right, so H is determining whether the program on the left will halt with the input on the right.
H is a nice machine, but can we really build it? We'll now prove that its very existence is logically impossible. Let's assume that H does exist. We'll place it on this stand for reasons that will be made clear in a minute. Recall that we assume H solves the halting problem perfectly. It should always print the correct answer. We are about to put this to the test. This is a photocopying machine. It simply prints 2 copies of its input. We'll place it behind H. Here's another simple machine. We call this one the negator. When the negator receives the words "not stuck," it gets stuck. And when it receives the words "stuck," it does not get stuck. And it prints a smile. We'll place it in front of H. Let's wrap it all in a neat package we call the X machine. X has 1 input and 1 output. Let's draw its blueprint. As before, this blueprint fully defines X. What do you think will happen if we feed X with its own blueprint? Will it get stuck? Let's find out. P simply duplicates our input.
P is
H
photocopy.
receives 2 copies of the blueprint of X. It should now determine what happens when X is fed with its own blueprint. Let's assume it says, "not stuck." N negates that and gets stuck. So feeding X with its own blueprint causes it to get stuck. But H said it wouldn't. H was wrong. Let's try again. This time, we'll assume H says, "stuck." X didn't get stuck. But H said it would. H was wrong again. But H is supposed to always be right. This is a contradiction, proving H cannot exist.
Okay, I hope everyone liked that. Bring back the. Okay, but I thought Windows uses the halting problem. It tells you no responses for some process. Yeah, okay, so again, it's possible to look at specific machines and determine whether they are stuck or not. You can't devise something like this in general because the problem is it can't analyze itself. All right, so that said, this is not, we're not really discussing halting problem. Halting problem is discussed extensively in CS 320, generally speaking. All right, this is what I mentioned before is another example of an unsolvable problem, the Diophantine equation problem and the halting machine. And to prove it, you use something that looks like this. All right, here's the video that we just watched. All right, so don't worry too much about that. Again, this is not a question in our course about halting versus not halting. Solvable versus unsolvable. The issue is the problems that are solvable. We know how to solve them. We solve them, use brute force, exhaustive search, but they do not have good solutions. They do not have efficient solutions. They do not have tractable algorithms. Okay, so we're going to now talk about two ways to break down a problem. One's called an optimization problem, and the other is called a decision problem. An optimization problem is a problem that you want to minimize or maximize some kind of objective function, right? For example, in the knapsack problem, we had a knapsack, it has a certain capacity, and want to know what's the maximum value of items that we can fit into the knapsack without it breaking, right? So that's an example of a maximization problem. A minimization problem would be, what is the minimum cost of a spanning tree, right? So it's got to span all the vertices, and we want it to be minimum, or what is the all pair shortest path, right? Those are minimization problems. So that's an optimization problem, right? But a decision problem means I don't necessarily need the best answer, the min or the max. I just want to know, can it be done in this? For example, in the case of a knapsack, I want to know, can I get at least $100 worth of goods into the knapsack? Can I get a minimum spanning tree that is less than 50, right? So those are examples of decision problems, right? The answer is yes or no. It's not a number, right? So this is going to be an important distinction in terms of, what we're going to do now. All right. So one of the things that we're going to discuss today, and there'll probably be a question related to it on the exam, is how do we prove that a problem is an NP complete? So the first step is knowing how you do it, and then the next step is actually doing it. So the first part is showing that it's in NP, and that's usually pretty easy to do. Because what does that mean? Well, either it means you can solve it non-deterministically, like by guessing, or another thing you could do is show that you can verify it. So remember what I said about the graph coloring before, right? Even though it may be hard to produce the coloring with 4 colors or 5 colors, whatever it takes, if someone says to me, here is the graph and here is the coloring, right? You color it, this one's going to be blue and this is going to be green and this is going to be red. This one's going to be blue again. They give you the coloring. I can verify in O of E time, right, that the coloring works or that it doesn't work. So that's what we call verify it and deterministically in polynomial time, right? So this step here, prove that it's in the class NP, is usually easy to do. The part that's hard and requires some creativity is showing that it's an NP hard, because in NP hard, you're showing that it's at least as difficult as the other NP complete problems. So the strategy for that is what we call a polynomial time reduction, which means that in polynomial time, we can show that the problem we want to solve, that if we could solve that, we could also solve problems already known to be NP complete, which means that if we can solve that problem, we can solve every problem in NP complete, because if it's NP complete, that means it's at least as hard as every other problem that's there. Okay, and given that that's not true, because we know that you can't do that, so then it's considered to be NP complete as well, right? So this is the basic idea, okay? So let's read this together. One proves a problem is an NP complete by reducing it, by reducing a previously known NP complete problem to it. So here is an example, okay? This is an easy example to understand. Unfortunately, many of the other examples are not so easy. So I'm just going to move the chat box out of the way. All right. So let's say we have already established that a Hamiltonian circuit problem has been established to be NP complete. Anyone know what the Hamiltonian circuit problem is? So that's going to be an important problem today, and it comes up again when we do backtracking sometime between now and the end of the semester.
It's a graph coloring problem.
It's not coloring, no. It's a graph problem, not coloring. What do we want to do? We want to visit every vertex once and only once before we return home, right? So you start at the beginning, wherever the beginning is. You want to visit every vertex, right? And you come back. So obviously you can't repeat edges, but not only can you repeat edges, can't repeat vertices. So it's a little different than the Eulerian circuit problem. The Eulerian circuit problem is actually can be done in polynomial time. It can be done in a very good polynomial time. You're allowed to repeat vertices here. You can't repeat edges. Okay, so just write that in the chat here. Okay, so Eulerian circuit, and you should have learned about this in 220, which is prerequisite. So Eulerian circuit is a circuit with no edges repeated. Vertices can be repeated. Okay, in a Hamiltonian circuit. Okay, circuit means you go back to where you started. Circuit with no vertices repeated. And obviously also no edges repeated, because if you repeat an edge, you're repeating a vertex. All right, so again, Eulerian circuit has a very good polynomial time. So EC has a polynomial time solution. It's actually O of B plus E, I believe. And Hamiltonian circuit has no known polynomial considered NP complete. Okay, so let's assume that we already know that Hamiltonian circuit is, let's say we know that Hamiltonian circuit is already NP complete. So we consider the traveling salesman problem. Everyone know about the traveling salesman problem? You want to visit all the vertices, return back to the starting point in minimum cost. So each edge has a cost. The cost may be time, it may be money, it may be distance. It's something that costs us. So we want to know, this is a practical problem, right? You have a salesman, right, who needs to visit. They need to go sell whatever they sell in a bunch of different cities. They can't do it online. So they have to go visit each city, and they want to do that with minimum cost. So that's a real problem in computer science. So how is this related to Hamiltonian circuit? Well, if I were to change all the edges in the traveling salesman problem to a cost of 1, so what am I really asking? I'm saying, is there a path, a circuit with a weight of n? Because what does that mean? It means I'm going all the way around with a cost of n, because each edge is 1 and I need to do n edges or v edges, right? So here is the reduction, right? here is the Hamiltonian circuit problem. The question is, can I visit each vertex, come back home, and only visit each vertex 1? Here's traveling salesman problem. It says, can I go from 1 to each vertex, return back to 1 with minimum cost? But if all the edges have the same cost of 1, then I'm really saying, is there a Hamiltonian circuit with a cost of 4? Because what would that mean? It means I can visit each vertex and come back to 1 with a cost of 4. Okay, so if I could solve traveling salesman in general, then I could make as a special case, I could just change all the edge weights, right? So I changed my graph. We did that yesterday, right? We changed all the edges to infinity, all the zeros. So I could change all the non-zeros to 1. And now I have, and then I run traveling salesman on that, and that will determine whether it's a Hamiltonian circuit. So the answer is, if I can't solve Hamiltonian circuit in polynomial time, I also can't solve traveling salesman in Hamiltonian time. All right, so we have one particular problem that is very important in and of itself, but also because it is surprisingly related to many other problems. All right, so this is called Boolean satisfiability, or SAT for short. No relation to the college entrance exam by the same name, although I suppose if you're good at these Boolean satisfiability problems, probably will do well on the math part. I'm not sure if it'll help you on reading and stuff like that, but it'll probably help you on the math part. Okay, so although in a certain sense, if you get logic, so then you're also able to do a better job of reading and understanding what implications are and so on. All right, so just a little bit of background on logic, right? We have these things called variables. They're sometimes called literals, right? Literals can be either as is or with a not before it. Okay, so I'm using the tilde for a not, really usually use like this more angular thing that looks like a tilde. But we're going to use tilde because that's on the, tilde is on the typewriter, and the other one I have to find it. All right, we have or, and we have an and. All right, so remember, this is always true. So you call that a tautology, right? Because something or not something is always true, and something and something is always false. So we call that a tautology. All right. I'm sorry. No. Oh, let me say that again. This is a contradiction. Why is it a contradiction? Because it can never be true, right? You can't have something and the not something both be true. The or is always true, so it's a tautology. This we call a contingency because it depends on the values of x1 and x2. All right, so what does this have to do with what we're discussing? Well, Cook and Levin, okay? Cook and Levin are these guys that we just saw a few slides ago. Those are Cook and Levin, all right? So what Cook and Levin did is they proved that Boolean satisfiability is NP complete. What does that mean? It means we have these statements with variables, and the question is, can we assign values of true and false to the variables in such a way to make this statement true? All right, so basically it's saying, is the contingency true or not? Can we make it true? So they call it satisfiability. Can I assign values of true and false to the x's and the x1s and the x2s and so on to make the whole expression? Now, there are certain kinds of Boolean satisfiability, something called two-set, where every clause has just two variables. That actually is a solvable problem in polynomial time. The Boolean satisfiability that we're talking about is three-set or bigger. All right, so it's important to understand this. You may have seen this in 120 or 320. Okay, we have these expressions, and this thing here is called conjunctive normal form. Conjunctive normal form, right? Because it's a conjunction of disjunctions. So these ors here are disjunctions. And if we take the disjunctions and we add them together, so we call that conjunctive normal form. Now, what makes it normal? What do we mean by normal form? If you've studied databases, you usually have several lectures about normalization and normal forms. Now, by the way, in 320 also, what do we call that? Greibach normal form and Chomsky normal form. Remember that? That's the other CNF. But that's not what we're talking about here. What do we mean by a normal form? So normal form means we have a very specific format that we have to follow, right? So in 320, when you learn about Greibach normal form and Chomsky normal form, it means your production rules have a certain format. The left-hand side has to look a certain way. The right-hand side has to look a certain way. So over here, we're saying in conjunctive normal form, each clause has to have only ors. You can have nots, but you can't have any ands. You see that? All these parentheses have no ands in them, only ors. And then when we combine them, we use only ands, right? There are no ors between the clauses, only inside the clause. Okay, so we call that a normal form. Now, this is called 3-sat. Why is it called 3-sat? Because if you look at each of the clauses has exactly 3 variables. Does everyone see that? 1, 2, 3. 1, 2, 3. 1, 2, 3, and so on and so forth. So we can string together as many of these as we want, but within each clause, there are 3 variables, okay? More generally, if it's the k-sat problem, it means that each of these expressions has k variables, okay? But this is 3-sat, all right? So 2-sat is not an NP complete. It's actually an easier problem when there are only 2 in each. The other thing to point out is if something is not in 2-sat, is not in 3-sat format, I can make it into 3-sat format. All right. Okay, so this again was a particular problem, but it's one of many problems. So already as far back as 1972, Richard Karp presented a list of 21 problems that are NP complete. So these are just some of them. Okay, and there's a certain hierarchy. Okay, what's the significance of the hierarchy? That some of these problems are closely related to each other, right? But these are, again, that was his list 50 years ago, right? So already 50 years ago. By the way, where have we seen this guy before? Anyone recognize that name? As in Rabin Karp, right? Rabin Karp, 2 mathematicians. Rabin's the guy who likes the randomized algorithms, and we had Karp, right? So the string matching algorithm. So, but aside from being famous for string matching algorithm, he's also famous for his work on computational complexity. All right. There is a book. It's an old book already called NP Completeness. It's just a whole bunch of problems that are NP complete. Discussion of that. All right, here are some famous NP complete problems. Some of them are already on this list, some of them are not. These are important problems. You know, it's not just theoretical problems, but bin packing, for example, is a important problem in real life. Anyone know what that is? So there's the graph coloring problem that we talked about before, right? If I have a graph, how many colors do I need? So what happens if it's not planar, or I don't know if it's planar? So what is a bin packing problem? Anyone heard of that before? I'm going to spend half a lecture just on that one, not today. So the bin packing problem, this is a real life problem. We have a bunch of containers, okay, like shipping containers. Well, it's not just packing as much as you can in a bin. I have a lot of bins, and I need to put as much as I can in the bin to minimize the number of bins. So imagine you're traveling overseas, and the airline charges you $100 per suitcase. So you don't really want to take more suitcases than you have to, because every suitcase costs money, right? So you want to fit as much as you can into the suitcase, but there's another rule, right? Suitcase can't weigh more than 50 pounds. So there's a limit. It's not just how much your suitcase can stretch, right? So you can't get a duffel bag that is arbitrarily large and put 500 pounds of stuff inside it, right? So there's a real life This is oh, you wear it on, right? So you wear like 10 winter coats onto the flight, right? Yeah, that's what some people do. Okay. And then you got to take them all off when you go through security. Like, that's a pain. All right. And then you forget. The last time I flew, my family bought me a little pocket knife with my name Lawrence on it. And the last time I flew in April, they took it away from me. So I guess that's what happened. So, all right. Okay, so these are important problems, right? We'll talk more about bin packing when we do bin packing, but I just want you to understand, some of these seem like sort of theoretical, but some of them are practical problems in industry. Okay, so one of the interesting problems that is NP complete is called the vertex cover problem, right? What is the vertex cover problem? Then I'll tell you why it's relevant in real life as well. So we want to know if I have a certain subset of the vertices, right? Do they cover all the edges? In other words, is every edge somehow directly adjacent to one of those vertices or more, right? So first of all, let me make sure you can all see the picture. Everyone see the picture there, right? What does the vertex cover in this case? I'll give you
Red and white.
Well, it's not the colors, it's the 135, right? The vertex color is 135, the ones that are red, right? Because if I have those subset of vertices, then every edge in this graph is adjacent to one or the other. Can someone come up with a real life scenario where such a thing would be important? So let's say you want to install security cameras in different rooms, and some rooms can see into other rooms, right? So you want to know, if I put the security cameras here and here and here, right? And assuming that an edge means I can also monitor what's in whatever is adjacent to me, right? So if I can put a security camera here and here and here, it means that all the vertices essentially are being covered, right? See that? Because if I can see into 7 and I can see into 6 and I can see into 5, well, the 5 is already going to be separately covered, right? So we call that a vertex cover problem, right? It could be a food service, it could be connectivity, wireless connectors, right? So there are a lot of situations, but this is a real problem as well as being an interesting theoretical computer science problem, right? So the question is, okay, so is this a polynomial time algorithm? Is this NP complete, right? What do we do with this? All right, so we're going to find out more about that in a moment. Okay, so let's assume that we already know that 3 set is NP complete. Okay, so we accept the results that Cook and Levin proved back in the 1970s, that 3 sat or higher, 4 sat, 5 sat, and so on, are all NP complete problems. We're going to take that as a prerequisite. Okay, the question is, can we use that to prove that vertex cover is also NP complete? And we're going to go through a proof. It's a little complicated. Good news is you don't need to prove, something this complicated on the exam. But I want you to get a feel for how these kinds of proofs work. Okay, so we call this a polynomial time reduction. And basically, what we're going to do is we're going to show that if I could solve vertex cover, then I could represent vertex cover as a SAT problem, right? In other words, I'm going to come up with a complicated, formula here. I'm sorry, I'm going to represent the formula, the 3 set formula, as a graph. And once I represent it as a graph, if I can solve vertex cover, then I can also solve I'm effectively solving the 3 set. But we know that 3 set is not solvable in polynomial time. It's an NP complete problem, which means that I really shouldn't have been able to do vertex cover either. Okay, so here is our starting point for 3 set. Does everyone see why this is a 3 set problem? Because what do we have? We have these clauses, and the clauses have 3 variables each. Okay, so the first clause has 1, 1, 1, 2, 1, 1, 3. The second clause will have 2, 1, 2, 2, and 2, 3. The last clause will have M1, M2, and M3, right? So those are the variables. Some of these may be negated, some of them may not be negated, right? So that's built into the use, whether they are negated, all right? So just to be more clear, the original variables are X1s, X1, X2, and so on. What we're doing here is we're taking variables from the set of variables and we're either using them as is or negating them. So U is our 3-sat clause. Again, in conjunctive normal form, each expression has 3 variables, and we have a whole bunch of expressions, M expressions, each of them with 3. Okay, so this is where it gets a little bit complicated. Okay, so this particular example comes from this book over here, which is the book I use for when I teach 320. It last summer and many times before, apparently not this summer. Okay, so what are we going to do? Well, what we do is we're trying to represent this 3-sat problem as a graph. And in order to do that, we start with, we have basically 3 kinds of edges. Okay, the first kinds of edges connect each variable with the negation of the variable. Okay, so this is an edge, right? I don't know if it's obvious to you, but this is basically an ordered pair. It's a tuple, right? What's an edge? It's a tuple. So we're saying for each variable in the original set of variables, right, we're going to create an edge for the relationship between the variable itself and its negation. So how many edges like that do we have? We have n of them because they're n variables, right? Next, we get to what they call the clausal arcs. What are the clauses? This is a clause. From here to here is a clause. From here to here is a clause. How many variables are in each clause?
2.
No, look again. How many variables? A clause begins here and ends there. What?
3.
3. And if it's 4-sat, there'll be 4. If it's 5-sat, there'll be 5. Right? So in conjunctive normal form, each clause has the same number. Okay. Fine. Now this is 3-sat. That's the one we care about for the next 5 minutes. The only problem we care about is 3-sat and vertex cover. So each of these clauses has 3 variables, and we have special set of edges that represent that. Okay. So what are we saying here? We're saying one edge corresponding to the relationship between U11 and U12. One edge for the relationship between U12 and U13, and a third edge for the relationship between U11 and U13. So that's what we're saying here, right? For each clause, I'm going to add 3 more edges. Yeah, 3 edges corresponding to the 3 relationship between the pairs of vertices, the pair of variables in here. All right, now we have what do we call these? The L are, what do you call them? The links? No, what do we call them here? What is the link? Yeah, the links. Okay. Okay, so we call them the links. Well, what is the links here? So the link is a relationship between a variable in the clause and the original variable. Okay, so let's go back for a second. Right, so let's say over here. So let's say U11 happened to be X5, okay, because we don't know what variable this is. This is just a placeholder. So let's say U11 is X5 and U12 is X4. So we create a link between U11 and X5 and a link between U12 and X4. So each of these is a variable. So we create a edge representing, this item in the clause with the original underlying variable. So that's what this does, okay? And you need to have one of those for each element in the clause and to do that for each clause. So how many of those are there going to be? Let's say there are 10 clauses, there are going to be 30 of those. Okay. So more generally, can someone give me a formula for, as a function of M and K, guess it's a function of n, m, and k, right? How many edges are we going to have? So there's n, the number of vertices. There's k, which is the version of set, which is how many things are in each clause. And there's m, which is the number of clauses. All right, so you can write in the chat. I'm writing it in the chat also, right? So we have 1 times n plus 3 times m plus 3 times, or let me say it differently. It's k times m plus k times m again. Okay, so that comes out to be n plus 2km. All right, so that's the number of edges. It's a lot of edges, by the way. All right, so now if we put those edges together, we have a graph. So we take all of our T edges, our truth edges, our clause edges, and our link edges, and we put them all together, and we get this. Okay, so what is the significance of this? And the answer is, well, now what happens if we try to do a vertex cover on this? Okay, can someone remind us what we mean by vertex cover? That was already a few slides ago. So what do we mean by VC, vertex cover? Today, VC stands for venture capital, but in this course, it stands for vertex cover. So
To
essentially,
cover all
yeah.
the vertices.
well, it's a subset of vertices such that every edge will be covered on one side or the other, or both, right? There's a subset of vertices chosen so that every edge will be adjacent to at least one of those vertices. So what does this have to do with this? Well, if we can do a vertex cover here, we can find a set of the x's, right, so that every edge is covered. Then we've made it satisfiable, right? We figured out a way to choose what the value. Remember, each of these x's needs to be either true or false. So that's what we're doing, right? If we can't solve this, we can't find a way of making each of these variables either true or false, right? And satisfying, you know, all these things that are here, then we can solve it. So the takeaway here, again, I'm less concerned with this proof, but the takeaway is so you understand the basic concept. The basic concept here is I have a problem that I don't know whether it's NP complete or not. So what I do is I take a problem that has already been determined to be NP complete, let's say 3-set, which was proven by Cook and Levin back in the 1970s. And I say, well, if I can solve vertex cover, then I've effectively solved 3-set as well. And we know that we can't solve 3-set in polynomial time, or at least not without being able to solve every problem in polynomial time, right? So what we're doing is we're taking our vertex cover problem, and we're taking our 3-set problem, make it look like a vertex cover problem, which if we could solve that as a vertex cover problem, we could also solve 3-set, which we know you can't do. All right. So this process will become a little more it'll become a little bit more clear when we do some other examples. Okay, so here's something called set cover. Okay, what is a set cover? Set cover sounds a little bit like vertex cover. It's a bunch of subsets Right, so Daniel's asking if we can solve the 3 set, not 3 set, it's called 3 set, but like, right, it stands for satisfiability. It has nothing to do with the word set. So we can solve 3 set, then we can solve vertex cover either. Right, because if you could solve vertex cover, then you could solve 3 set. So since we know you can't solve 3 set, it means you can't solve vertex cover, correct? All right, so what is set cover? Set cover says, okay, if I have a bunch of subsets, right? All right, which subsets can I use that will cover the universe? Okay, so let's say I have these subsets here, right? S1, S2, S3, S4, and I want to know which one will make a set cover. So it turns out that S1 and S3 make a set cover, right? Because if I take S1, which has these even numbers, and I have S2, I'm sorry, S3, which has odd numbers. So if I put those two together, I perform the union of them, I now have everything that was in my original set, my universe set. So that is a particular example. The question is there a polynomial time algorithm that will solve this? And the answer is we're going to prove that there isn't by showing that it's related to another problem. Anyone remember this problem?
Professor,
Yes.
for set cover, do the sets have to be like mutually exclusive? Meaning they don't have any
No, they don't have to be mutually exclusive. So let's say S3 also happened to have 6 in it. That would still be okay.
Okay.
You're asking if they have to be disjoint, if they have to be partition. The answer is no, not for set cover. For a partition would have to be. All right. Okay. So what we're going to do now is we're going to show how vertex cover and set cover are related. Okay, so how do we do that? So what we do is we take our vertex cover graph and we're going to represent this as a set cover problem. Okay, so let's see. Okay, so our universe is just the set of edges. Okay, so our universe here, we've got a 1, 4, you have a 1, 2, you have a 2, 5, you have a 2, 3, we have a 3, 5, a 3, 6, a 5, 6, right? You get the idea? So for every edge in our vertex cover problem becomes the universe. All right, now, what about the subsets? So the subsets are per vertex. Okay, so it's almost like the neighbors, except instead of it being the neighbors, it's the edges that are 2 neighbors. So our first subset is going to be 1, 2, and 1, 4. Our second subset is going to be 1, 2, 2, 5, and 2, 3. Again, we don't care about the direction on the edges. You see that? So for each vertex, we say what are the edges that are incident to it, right? So that's what this is doing. It's saying S2, S3, right? Because there's 1, 2, 3. 3 is going to have 4 in it, right? So I don't know if you can see that. I got my chat box in the way. I'm going to move the chat box out of the way. So we have 4 edges. Okay. So what does this have to do with set cover? Well, I'm basically asking, is there a set of these vertices in this graph which now correspond to subsets, so that if I look at all the edges in the individual subsets, put them together, I get my universe. So if I could solve the set cover problem, I could also solve the vertex cover problem, which we've made to look like a set cover problem. But since we know from earlier slides today, right, that vertex cover is related to 3 set, which is NP complete. Therefore, vertex cover is also NP complete. We know we can't do vertex cover. So if I could turn vertex cover into a set cover, then I could also solve set cover. So apparently I can't solve set cover either, right? So that's the sort of the gist of the way these things work, is you convert one problem into an instance of another problem that we know we can't solve, right? So again, we're taking our vertex cover, making it look like a set cover, which means that if I can solve set cover, I can solve vertex cover. We know we can't solve vertex cover, so apparently set cover is also a problem. So it's important to understand the terminology. We call this a vertex cover to set cover reduction, right? We're taking a known NP complete problem and making it look like an instance of the new problem. And since we can't solve the NP complete problem, therefore it must be we can't solve this new instance of the other one. All right, so I want to take a step back to an earlier picture from today. This picture near the beginning of today's lecture, all right? Everyone see this picture? By the way, this picture is true whether we assume that NP equals NP or we assume that P is not equal to NP. In both cases, there are problems that are in NP hard, right? Because we said NP hard is at least as difficult as NP, right? So there are problems that are in NP hard that are outside of NP complete in this case, or yeah, they are outside of NP complete here, okay? I'm sorry, they are outside the NP part of NP complete. Okay, so that's the question now. What kinds of problems are there? So you partially know the answer to that already. So again, the question is NP hard, but not NP complete.
All unsolvable
In NP. What?
all the unsolvable problems will be in there. Like
Okay, good. So as a starting point, any problem that's unsolvable is not in NP, because NP means it's solvable non-deterministically in polynomial time. It's also solvable deterministically in greater than polynomial time, right? But it is solvable. It means if we add a machine that could do, factorial, number of operations in a short amount of time, we could solve it, right? So that's the obvious answer. The obvious answer is all those unsolved problems, like the Hölting problem, like the Diophantine equation problem, all the things that are dependent, like they call the busy beaver problem, the blank tape problem, right? Problems that are dependent on the Hölting problem. So those are all in NP hard, but we have other ones as well. So I just wanted to mention them too. All right, so if you look on the bottom of this slide, right? So here are Hölting and Diophantine. We have problems that are difficult, okay? We have optimization of TSP. So the decision problem for TSP, TSP stands for traveling salesman problem, that is NP complete, okay? The optimization problem, which is not just determining if I can do, get a solution in 100 or less, or 50 or less, or 1,000 or less, but actually finding the best possible answer, which sounds more difficult, right? It's not just a yes or no, but I'm actually trying to optimize something, or what we call, we have another example here of the degree constrained minimum spanning tree, which means I have a minimum spanning tree, but I'm also requiring, which we learned about, we had a whole lecture about that, Kruskal and Prim, but imagine that it's degree constrained. What does that mean? It means I don't want any nodes that have more than X, X edges. Why would anyone want that? In practice, in real life, why would that be a real concern? So remember, minimum spanning tree is often used to represent a networking model to make sure that all the devices are connected. It could be for utilities to ensure that water can reach all the different houses, or natural gas can get to all the houses, or electricity, or phone, right? Anything that is provided on some kind of a network, not necessarily an electronic network, right? So we want to ensure that it can get to everywhere, it's all connected. So why would we care about it being degree constrained? So just think about, let's say a node is a house, right? There's only so many, gas lines they can have coming into a house. The space is finite around a house, right? Also, if you've got, think about a star graph for a second. Everyone remember what a star graph is? What does a star graph look like? It doesn't really look like an American star. What does it look like?
Every vertex is connected to a middle vertex.
Yeah, so on the keyboard, which key on the keyboard does it look like? There you go, Chen got it, right? The asterisk, looks like an asterisk, okay? You got something in the middle, you got all these things coming out, okay? Why would a star graph is a spanning tree, right? It's a spanning tree of a network, everything is connected. Why might it not be the best model for a network?
I mean, usually you dump like a bunch and it's not all.
Okay, so if the center is down, right? So that's a problem. Okay, a lot of server models, client server models work exactly like that, right? The server is the center and everything else is on the outside. If something goes down, right? So that's a problem. Okay, but it could also be used even if you don't have a server. If you just have a networking model, maybe one computer is in the middle somewhere. So that's a little bit risky. All right, so the motivation behind a degree constrained minimum span tree might be to say, you know what, I don't want too many, any one vertex to be responsible for too many edges. Okay, it's a risk. Okay, it may be physically dangerous. It may be there's just not enough space. Okay, you may not have that many ports. So let's say every device in the network is equipped with some kind of switch and enables that, or a hub, right? Something that allows you to have connectivity. There's only so many ports on the hub, right? So that could be another issue, right? But again, there could be a risk factor of having, so that's, again, that's not really important here. What's important is that you understand for this purpose, that here's an example of a problem, which is just a variation of a problem that we not only discussed in our class, but we had very good algorithms for them. Prim's algorithm, Kruskal's algorithm are very good algorithms. They can be solved in, below n squared time, which is very nice. Okay, it doesn't get much better than that. But yet, if I constrain the degree, all of a sudden we get a problem which is, exponential time, even in a non-deterministic model where guessing is allowed, it's still exponential time. Okay, another example there is chess. Right, so chess also, there's so many different possibilities that's considered exponential time. Okay, by the way, so how do you have computers like I forget what they call it, the one IBM had, right, that played the chess player. It's called
Watson.
It was called Watson, right? It was called Watson. Okay, so how do they work? If you're telling me that chess is exponential time in a non-deterministic model, right? That's with correct, correct guessing all the time. So
Well,
how do you build a machine that plays chess?
well, it can give approximate answers and
It gives approximate answers, right? It doesn't necessarily find the very best. That's why, by the way, in that video we watched, right, it said it can play checkers. Right, it didn't say chess. It said it can play checkers and always win, right? So it will probably always win in chess at this point, but that's because even if it's not giving an exact answer, it can still look ahead beyond what most humans are able to do in the same amount of time. All right, so again, there are problems aside from the unsolvable ones that Ellie mentioned. There are solvable problems that are still beyond NP complete. They are in the NP hard category as well. And I think that's my last slide here. So we have about 10 minutes left, and I will entertain questions. I will entertain questions about today's lecture, entertain questions about any assignments that you're working on, entertain questions about the final.
yeah, I mean, for assignment 6, I know we had the discussion
Professor,
Black, but I was a little unsure.
That's the string matching one?
We had found the pattern in the string.
Yeah, string, oh, yeah, string matching, right, string search, okay, yes, go ahead.
I know you told us to treat the entire file as one big text.
Okay, so just in response to you, David, so I still have to mark some other ones, so yeah, until I get to them. Yeah, you figure you have time. Okay. Back to you, Ellie. Yes, go ahead.
Oh yeah, I mean, I don't know. Did you ever on Slack? It got like a little, I don't know, weird. Because if you do that, it'll only return the first value of the, like the word it finds, which only gives you like 6 things to actually, like check.
Okay.
But the way I did it, I did line by line, so you get like a lot of tests, I guess.
You did line by line on the pattern?
Yeah, I checked each line for the 3 patterns.
Yeah, so the pattern, the text, I'm sorry, the text is one text. The text is one text. So if you only find the first one, you only have to find one. That's okay.
Okay, then my graph will only have like 3.
That's fine.
Okay,
Text is a string. Yes, text is a string and pattern is a string. Okay, but the pattern file is a few different patterns to look at, and the text is one big text.
Then should I resubmit? Is that a thing?
I mean, it'll probably be fine, but yeah, if you want to resubmit it, you can resubmit it. You know, I always look at the last one submitted when I get to it.
Sure, thanks, Professor.
Okay.
Professor.
I'm not so interested in what the answer to the search was. I want to see, okay, did you get the algorithms working? Are you able to represent the information in a graph? Are you able to represent the information in a table? And it doesn't really matter so much, but my intention is that the text be one text and that you have a few patterns to search for. Someone else was asking questions, sorry.
Yeah, I volunteered yesterday, but I think I might have missed the top hat.
Okay, so we'll take care of that offline.
Okay.
Regular expression in exam. So regular expressions per se, I had just a little bit about that. No, realistically, no. So in terms of the exam, again, there will be a divide and conquer recurrence, guaranteed. Okay, so make sure you know how to do that. A lot of old exams have examples. A lot of them have solutions with it. So you can be sure that there's going to be one of those. I also told you there's going to be one question about how do you measure empirical performance. So it's going to be essentially testing whether you understood the pattern, not pattern as in string matching, but the pattern, across pretty much all the assignments this semester, right? What do you do for a new problem, right? So that will be on there. There will be a question, something to do with dynamic programming. There will be a question on NP completeness with a second piece of that is, what do you do if you can't solve it in polynomial time, right? So that, will get us to another lecture on approximation algorithms, right? Also any, themes that recur in the class. So things like not just sorting in and of itself, but the impact of sorting on other algorithms, the role of data structures in algorithms, the role of randomization, right? Parallel computing is a nice kind of question because it involves understanding a serial version of a problem and then what you can parallelize and what you can't. So those are some of the kinds of things that we're looking at. Okay. When you say one question, it's like 10 points or a question mark. So there'll probably be, again, the exam, I don't know if I said this, exam will be broken up into 2 parts so that if you want to use the bathroom, the exam is in person at Queens College. If you want to use a bathroom, you want to go get a drink, you can do that in between. So we're going to have 2 parts. And we hand in one part, you take your break if you want. You don't have to take a break, and then you get your second part. So it's going to be within the 2 hours between 10 and 12. And I do have another class, not only have another class, I have another exam at 12 o'clock. So everyone needs to be done. And so each section will probably have either 3 or 4 problems. So I don't know, points, I'm not sure. It depends on how many it is, but it doesn't really matter. Yeah. Yeah. Okay. Other questions? Can I take absent for 355? So for those of you who are in 355, that 8 to 10 lecture will be delivered asynchronously. So you watch that video when you want, and there will be some review questions. Do I curve the final exam? That is a good question. So the answer is I don't necessarily curve the final by itself. I do look at the whole course. And the way I work grades, I said this in 355, but I'll say it again. So the department not just recommends, but they take seriously that they want the number of A's to be between 10 and 30% of the class. Okay, so if I give more than that, I get in trouble and then I can't teach. So that's not good for me. And I guess it's up to you to decide whether it's good for you if I don't teach. But they want people who adhere to their guidelines. And it makes some sense because A is a grade for outstanding. And by definition, some people are outstanding and some people are not. Okay, maybe they're outstanding in other areas. All right, so what do I do? What do I do? So let me be more specific. So I take your grade from the semester according to the percentages that I set on the syllabus, which means 30% for what I call the sort of the review part, which is the Xi books and the review questions. I also throw in the attendance into that. So the attendance shows up in Top Hat, so that gets rolled into the Top Hat score. All right, and what I do with the Top Hat more specifically is I look at the total, the highest score. So let's say the maximum you could get on Top Hat. When I say Top Hat, I don't mean programming assignments that are in Top Hat. I mean review questions in Top Hat, right? So let's say the maximum person could have gotten was 400, but the maximum person anyone got in the class was 350. So I say, you know what, 350, that means that's a good score if that was the top student. So that becomes 100%. And then I do it relative to that. All right. Okay, so I calculate your average, including the final, and then I say, wait a second, you know what? I'm looking at the grades. So either I will see, sort of a very uniform distribution, and then I, pick a certain percent, regardless of what the actual score is. Or sometimes I'll see a whole. In other words, I'll say, you know what, 20% of the people, did in this cluster. And then all of a sudden there's a 5-point difference before I get to the next group. So I say, you know what, that's a logical break. So that's something that I do. So it's a kind of curve. Just keep in mind the following, that most students are doing very well on the programming assignments. Most students are doing very well on the review questions, not 100%, but they do very well. And the average score on the Xi book, the median score, I should say, the median score on the Xi book will probably be 100%. Okay, there are some people who are going to, for reasons I don't know, they're going to ignore that requirement or skip some chapters, but most students are going to get 100% on that. So it is the exam that is, plays a role in sort of differentiating the students here, right? Someone who, skipped half the programming assignments or decided not to do the Xi book for whatever reason, they're going to be at a disadvantage. All right. Some students are complaining about why. All right. So, well, let's see here. Someone's asking about other departments where 80% get A. That's just their department's policies. So what if half the class actually deserves an A? It's a fair question, but the reality is we can use some statistics here, right? So we have a large sample, and it's expected that a large sample will adhere to some, we call it the law of large numbers. So if we had a class of 3 students, it's very possible that the 3 students are outstanding and they are not representative of the population at large. When we have, 40 something students, it's going to be more closely aligned. So that's the reality. The reality is I have to adhere to the guidelines, and there's some logic behind it. It's not arbitrary, arbitrarily chosen. All right. Can the Zybook be optional? It's not optional at this point. I will say this though, there are many, it looks overwhelming, but there are many chapters there that have, I don't know why they didn't do it, but they did like nothing, no participation activities, or only 1 section out of 10 sections has participation activities. I will also tell you this, I am able to see how long each student spent on each chapter. And I have students who are completing entire chapters in a matter of minutes, not hours, minutes. Obviously hours includes minutes too, but I'm saying, 10 minutes, 15 minutes. So you may not get anything out of it that way, but doesn't have to be overwhelming. And it is another type of presentation different than mine. I'm going to venture to guess that very few people in the class are reading an actual textbook. So having this online Zybook experience is an alternative. All right, so let's see. VNA is asking a good question. Would it be possible to do an NP problem similar to one that could show up on the final? The answer to that is, I don't know if I'm going to do one necessarily, but I usually make it, you get to choose. So what I tell students is take a problem, not one of the ones that we did in class, and be prepared to present it. So I usually give you some discretion on that. Okay, so first of all, I expect you to know in general what goes into proving that a problem is NP complete. Okay. So you need to know that you need to prove that it's in NP, and you need to prove that it's in NP hard, right? So those 2 pieces. And then I usually say, choose a NP problem that is not NP complete problem that is not one of, and I'll specify what they are, not one of the ones we actually did in class, and prove that it's an NP complete. So it's an opportunity for you to look now when you have access to the internet and so on, find one that is easy enough to understand that you could reproduce during the exam. Okay, and then the other piece of that is usually coming up with an alternative, right? So given that it's NP complete, what can you do instead to try to solve it? All right, we have a question here. The class VID is not working for me, the one uploaded yesterday. I didn't catch that. Oh, video? Was anyone able to? Can someone write yes if they were able? It's making me download. Oh, so just so you know, when you go to Google Drive, sometimes the image looks like me. It looks like I'm about to speak. It looks like, you actually see video. And sometimes it's red. And if it's red, I think that means that Google hasn't finished processing whatever it does, so you have to download it. Right? So that may be the issue with yesterday's video. It may be still in that other mode, and it will eventually shift over. So if you watch it right away, yeah. If we missed a top hat assignment, can we submit it late? So when you say a top hat assignment, I assume you mean review questions. You always have at least 3.5 days, because they usually after the lecture. So the answer is no on that. Okay, because the answers become available. I don't know if you noticed that the answers become available, and it wouldn't really be meaningful to let people hand it in after they have all the answers there. So you can do all your clicking around to get all the right answers in Zybook, but the review questions in Top Hat follow a different model. If you miss one, it's not really gonna affect you. If you, consistently miss them, it will affect you. But, missing one is not gonna make a big difference.
Professor, can I share my screen?
Okay, well, before Ilma shares her screen, do we have any other questions about exams or anything like that? Okay, so Ilma, go ahead. Let me enable the screen sharing.
I have one question.
Yeah,
It's like for the class, I got an email from like to get a COVID test. Would that affect me next week coming in? Like, should I get it before?
Yeah.
so I can say this, you need to have access. So if you're being told that you don't have access, they want a COVID test. Well, I probably shouldn't be discussing some of this on recording, but you want to be sure that you're cleared. So
Okay.
if you're not cleared, you've got a problem, and it's not going to be so simple to resolve. Let me just show you something I have here before we go back to Ilma. Hold on, I'm just looking through my papers for the summer. Okay, so you want to have something that looks like this. Okay, cleared for CUNY access.
Okay.
All right. Yeah. Okay, back to you, Ilma.
Professor, should I run the program?
Well, tell me what the question is.
I'm passing two arguments in my process file function.
Okay,
I don't know how to, make my headers think that I'm passing two different text files.
okay, so go to process file. Go to the process file function. So we've got a pattern file name and you have a text file name. You're opening the text file, putting it in text, and then okay, so that just gets you the text and patterns back. All right, so now what you need to do, go back to the code. So you need to iterate over those patterns, right? So if you go further down, you're going to need to iterate. So you see you're saying text equal, look in line 198. You see you're passing in an empty string and an empty pattern?
Yeah.
Yeah, so you need to get the string. You might want to move your code around, right? But you want to be able to iterate over the text and the patterns, right? So you want something like, go to the line on top of it after the timing. And you either want to do this combined or separate, but you want to say something like for text, pattern in, right? And then you have your list of patterns, which you got back from the headers. So the headers of 0, I'm sorry, not headers, results of 0. Sorry, results of 1. Now, again, because of where you put it in your program, you don't have that. So you may need to store that so you have it further down. You understand what I'm saying? Because you're getting your text and your patterns in line 186. Here's another thing. I would do that outside line 186. You could probably do that right at the beginning.
This whole line from 198 to
No. That one thing, you could get your patterns and your text up front. Here, what you really want to be. You need to iterate over patterns. Here, I'm gonna here, I'm gonna write in the chat here for a second, okay? So you're gonna do something like this, right? For text in text, and then indented, you're gonna say for pattern in patterns. And then indented in that, you're gonna say for alg in algs. Okay, it's not indenting, but those are nested loops. Okay, so for each L, you're gonna say, you're gonna do your start time. So this is inside the nested loop. Start time equals the time. And then you're gonna call your alg, and you're gonna call your alg on your text and your pattern. And then you're going to get your end time. Again, the indentation isn't reflected here. Equals time. And then you're going to get your net time equals the end time minus the start time. And then you take that net time, so place net time into dictionary for the or dictionary or table. Well, it's actually both, right? It's the dictionary and table for that text, pattern, and elf. Okay, so that's the hierarchy. So again, all that code there is inside a triple nested loop.
You also don't need sizes anymore because we only have 2.
Right, the sizes are not relevant here.
Are you gonna get some errors where you have to replace, like for the dictionary, we use size as the second option there. You have to make it like 0
Right.
and 1. Something
Okay,
like
so
that.
what you can do is, you can build up, either a dictionary or a table. Don't worry about the text table at the beginning. Do that at the end. Okay, so take all your times, and your algorithms, and your strings. Put that all into a regular Python, multi-dimensional list. Then when you're done, use that to feed the table. So I wouldn't try to make the table and output to the table in the middle of the loop. Do that at the end. Just like with the other assignments, we did our data frame at the end, right? We built up the data, but the data frame we did at the very end. Okay, so where's you have your,
somewhere here.
so you're gonna want to have, go up. So you need to have a triple nested loop. So the order can change. In other words, you could do for alg and string algorithms, and then you can do for text and text. You know what? Maybe just read in the 2 texts as 2 texts. So call instead of process file like you have when we did in class, do this. You could say text1 equals read file. Let's say it's called text1.txt. And then you say text2 equals read file text2.txt. And then you can make a variable called, right, because we only have 2, so you could just do it like this. You could also make it a loop if you want. All right, so now you have your text. And the way you get your patterns is you read okay, now you have a list of patterns, so you iterate over them. Does that help?
So I iterate using a for loop.
You need
For
you
text.
need a threefold for loop, right? You're iterating over algorithms, you're iterating over text, and you're iterating over patterns. Now, What I wrote in the chat was to put the algorithm on the inside. You can do the algorithm on the outside. It doesn't really matter as long as you have the nested loop.
I'll take a screenshot.
What are you taking a screenshot of? The chat?
Yeah, but where did it go?
But don't take a screenshot. Just don't you have a chat
Oh,
log?
okay, okay.
Just grab it from the chat log. That'll be better. Okay, so again, you have 3 nested loops. Those are going to be indented inside each other, right? Now you can put the alg on the outside if you want, or you can put it on the inside, but that's you're iterating over all 3 of those. Okay, so let's just be clear. Take those lines 220, stop. Go back down. Move lines 229 through 232. No, 229 to 232. Move them to the top before the for loops, not over there. You do that later. Just go to the pseudocode I just gave you. Go down. Take lines 229 to 232. Undo. 232 to 229. Grab those 4 lines, please. Okay, move them before that for loop of pseudocode. Good, because you need to do that up front, okay? Now, it's indented, right? So for text and text, for pattern and patterns, the pattern is inside a text. The alg is inside the pattern. If you prefer, you can move the alg to the outside. It doesn't really matter the order of the 3 loops, as long as but it needs to be indented. Does that make sense? Yeah?
Yeah.
Okay.
I was getting errors in my headers. Like it's saying that my array size is supposed to be 12 elements.
That means your list is probably messed up. In other words, you have a list with how many column headings are you supposed to have? 6?
I said I'm going to have 4 over here.
Okay, so you have 5 over here, right? In line 197.
Yeah, but
That's a
the
problem.
alg is a variable.
But you can't have 5 headers and 4 columns. And alg by itself also doesn't work. You would have to say alg underscore name. But that's not your header. Your header is string algo, right? Then the value, which is going to go into the table, is going to be the name of the algorithm. The header is string algo. Yeah?
Yeah.
Okay. But I don't like, something's confusing here. So you don't want to have headers where 2 of them are the same. So the string is what? Don't call it a string, call it a pattern or a text. Which one is that?
Pattern.
Those call it pattern. Okay. And instead of length, okay, so if you say length there, it's pretty clear that that means the pattern length. So what is length, the other length? Is that the text?
It's the output, like from the text.
It's the position?
Yeah, position.
So call it position then. All right, we also want to know which text it is, right? But when you're building this table, unless you have 2 separate tables, but one knows it, if the text is too big to actually put there, we could say text, call it text 1 or text 2. So I would create another file for that unless you have 2 separate tables. So I would put that at the beginning so we know which file it is, right?
In these,
No, yeah, but I'm saying you want to know, let's say, the file name.
I'm passing in the file name.
I'm
over
saying
here.
make it, yeah, but no, but I'm saying in your data, when I'm looking at the results, and let's say you found a pattern, I don't remember what the patterns were, let's say it was free. Well, free in which file? Free in the text 1 or in the text 2? So that should probably be one of your headers also, right, to identify which file it is. Does that make sense?
How do I do it?
You just add to your list of headers. So just create another column. So at the beginning, I would do it at the beginning, right? No, not that beginning. The beginning of the list of headers, I would say the text. Okay, no, go to line 197. 197. No, go to the beginning of that line. No, not a new line. Undo. At the beginning of the headers, headers equal, create another column called text. No, not another list, another column. So inside there, right there, call it text. And just to be more clear, create another parameter called text length. Call it text length, good. And then change the length after the pattern, just so we know what we're talking about. That's going to be pattern length. And then you got your algorithm there, fine. And then you got the position that it found, that's good. So now make sure in line 199 and 200 that your alignments and your data types match up. So you're going to need to have 6 of those instead of 4, and make sure that, you know, the data types align as well. So you have text, integer, text, integer, text, integer. You need to have 6. Okay, unfortunately I have to go to class. Okay, the good news is I have a lot of grading to do, so I'm not going to get to 6 for sure, not today. Maybe tomorrow I'll start. Okay, I have to go to my 12 o'clock class.
Thank
All
you,
right.
Professor.
All right. Okay. Take care. Bye-bye, everyone. Bye.